Our next topic in this chapter is modular programming. Modular programming means the approach of dividing computer programs into small subprograms or modules that can be developed and tested separately. So modularity means actually that having some pieces, and by combining them we can reach the final complete conclusion. And this can be implemented in programming as well. We can have some small pieces of codes and we can combine them to be able to have the final complete code actually. And this makes things easier. And modules are as independent and self-contained as possible so that we can use them in a generalized sense. In standard high-level languages such as Fortran 90 and C, the primary programming element used to represent each module is called procedure. And there are two types of procedures, functions and subroutines. Functions usually returns a single result, while subroutines returns several results. So these are two types of procedures that we use, and usually the functions are the most general ones. And much of the programming related to software packages like Excel and MATLAB involves the development of subprograms. And in Excel, the subprograms are called modules. In Excel, the modules or subprograms are called macros. And in MATLAB, these modules or subprograms are called functions. So because we will use MATLAB in this class, we will be developing some functions and modules, and we combine these modules or functions or call them to complete a final project or final problem, to solve a problem in a complete sense. So modular design has some advantages, or modular programming has some advantages. The use of small, self-contained units makes the underlying logic easier to devise and understand for both the developer and the user. And the development is easy because each module can be perfected in isolation. So we basically divide the problem into small pieces and make these pieces as simple as possible and also as independent as possible, as we mentioned before here, independent and self-contained. And this makes the programming easier. And especially for large projects, for large problems, different programmers can work on individual parts so that in different modules, different people can study, and in the end, with all of these modules, the complete project or the problem can be solved. Modular design also increases the ease with which a program can be debugged and tested because errors can be more easily isolated. So in each module, there can be errors, and you can simply go to that module which has error and solve it in that module instead of trying to solve in a very large program or software. Also, the program maintenance and modifications and updates can be easier with this way. You can simply update the necessary part, the necessary module, to be able to update the complete structure or complete program. Also, most importantly, when we develop our codes in a modular way, we can create our own library of our codes, and we can use them later for different projects, for different problems, by combining different modules, different functions to be able to address a problem or solve a problem. And this will be the philosophy or concept, our programming approach as well in this class, and we should be able to learn how to create modular programming. And in this slide, we will provide an example for modular programming, and we will use our known falling parachutist problem from chapter 1. As you remember, we had this numerical solution, Euler problem, or Euler method. Vi plus 1 is equivalent to Vi plus dvi divided by dt and delta t, and dv dt was g minus c over m and v. So we can create our own code for this specific parachutist problem, but instead we can try to use that modularity approach and try to generalize the codes as an Euler problem, for example. Then we can use that in the parachutist problem. So let's first define or remember this pseudocode specific to the parachutist problem. We defined this before, and you can see that we have our inputs, which are the inputs for parachutist problem, and then we have the calculation of dv dt and calculation of v, this formulation in this pseudocode. But instead of this, we can say that, okay, actually this problem or this equation here is an Euler method. And in the Euler method, we said that new value is equal to old value plus slope times step size. And we can simply generalize this as y equals yi plus dy dt times h. And actually this y also I plus 1. So we simply first create a modular pseudocode to be able to solve any Euler problem. So it doesn't have to be the parachutist problem only. It should be able to use for other problems as well. So that's why we create a function Euler as a modular pseudocode. And here we define t, y, h, do, and start with do. Actually, we make this do function. Over here as well, we had this. Instead of this, we will have a generalized function over here. And this y is the output, but here, if you remember, it was v. So here we make it general and called it y. And if we want to use this for falling parachutist, we will just define this as v, and that's it actually. And we call this earlier as the output, and we will just call this function to be able to solve the parachutist problem. In the parachutist problem, so we are calling Euler function, as you can see here. Euler function, this one, with the same inputs. We called it, but these inputs now are the inputs of the parachutist problem. Basically, these ones are defined as this, and the y here is the velocity. And over here, if you remember, we had this slope function, this one, and it was general here, so we can simply define a dy function for the parachutist, and we can simply call this here as a modular part. Then we simply calculate this in this general Euler function and find the velocity of the parachutist problem. And in this function, g, cd, and m are inputs, and it's just the formulation of this on the left hand side, and we finished calculation it. So eventually we call this over here calculate dy dt and calculate y and t using the inputs defined here, and this gives us y value, which is the velocity eventually. And with this way, we used this for the parachutist problem, but if there is any other problem, we can still use this Euler function. Just we need to define this slope function specific to the problem as another modular part. Then it's easy to, or straightforward to, use this Euler method. So this makes the programming very generic, and you can see that in this especially Euler function, there are no references to the specifics of the parachutist problem.